Okay, this is Chapter 2, Atoms, Molecules, and Ions, and let's go ahead and get started. This chapter is broken up into 4 sections. The first section covers early ideas in atomic theory. In this section, we're going to take a look at the postulates of Dalton's atomic theory. There are 5 of them, and we're going to discuss those postulates in relationship to the laws of definite and the laws of multiple proportions. Now, a little bit of background. The Greek philosophers, in particular around the 5th century BC, Leucippus and Democritus, come up with this term, atomos, which in Greek means indivisible, and they argue that all matter is made up of these small, finite little particles called atomos, atoms. And they thought of atoms as particles that could be recombined into different shapes and structures, and then could be joined together to make new things. But Aristotle, who came slightly after them, came to a different conclusion. He said that the 4 elements that make up all matter in the universe were made of fire, earth, air, and water. And the big challenge he conveyed to the atomists was, if that's in fact true, if you're saying all these things are made of these atomos, then prove it. And in essence, they could not do so. They really looked at this as more of a philosophical debate and never really kind of moved towards any proof of what they were, of their conjecture. So the Aristotelians really won out on this one, and for the next 2,000 years, or slightly better, we have followed the Aristotelian concepts of earth, air, fire, and water as being the 4 elements. And you'll see as you watch Chemistry of Volatile History and such, how some of that develops into other ideas through some of the alchemists through the 15th, 16th, and 17th centuries, and into phlogiston theory, and then how in the 17th and 18th centuries that starts to change. And we start to develop these scientific proofs as we move towards the turn of the 19th century. Now, moving forward into the modern day, we can see things such as like a breathalyzer. And breathalyzers can be more than just to test alcohol content. They can be a more sophisticated device that's set up in a laboratory setting or in a doctor's office, in which case certain diseases produce certain byproducts, some chemical byproducts that can be exhaled through the lungs, and a breathalyzer test or a breathalyzer type device that can capture what is being exhaled through the lungs could be identifying particular types of molecules, as you can see here, a variety of different things that we normally exhale in air. But if we start finding things that are foreign that shouldn't be normally exhaled by the average typical human being, they may be indicative of a particular disease that person may have. So taking a look at these, and literally your breath is turned into a mass spectral analysis, as you can see on the computer screen, which can identify the compounds or the elements that are being exhaled. And that can be a very, very good and valuable diagnostic tool for health conditions. Now, Dalton's 5 postulates really here are listed, and these are copied right out of the OpenStax text. And really the first sentence of each is really the main point, and then they give a little bit of an example afterwards. And on the next slide I have a shortened version of this, but let's go through it real quick. First, matter is composed of exceedingly small particles called atoms. 2, an element consists of only one type of atom which has a mass that is characteristic of the element and is the same for all atoms of that element. 3, atoms of one element differ in properties from atoms of all other elements. 4, a compound consists of atoms of 2 or more elements combined in a small whole number ratio. And 5, atoms are neither created nor destroyed during a chemical change, but instead are rearranged to yield substances that are different from those present before the change. Now here's a little briefer version of it I've got on the next slide. And it simply states the 5 postulates, again, restates them. Now, there's a couple things to remember about Dalton's atomic theory, the 5 postulates that he has. 3 of them really pretty much have remained intact as they were, as he developed them back in, and this was around 1807, so a little over 2 centuries ago. In addition to that, the 2 that he was unable to prove otherwise. Of course, he didn't have the character or the capabilities of diagnostically proving anything beyond what he was able to state here. But the two that were later proven wrong have been modified to create the new atomic theory. But one of the things, well, we'll talk about him here as I go through this slide. So let's just take a look at that first. All matter is composed of extremely small particles called atoms. Okay, that one's still intact. Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Well, the slight variation to this second postulate here is that we now know of isotopes, which are variations of an element, right? Of course, an element's determined by the number of protons it has. You remember that from physical science. And so an atom could have different numbers of electrons, but different numbers of neutrons, really, and that's really what you're looking at when you look at an isotope. So they could have a different mass, but still be the same element. So the second postulate here has been modified. Third postulate, atoms cannot be subdivided, created, or destroyed. So Dalton was thinking that the atom was the smallest thing there was. Of course, now we know we could break down an atom into protons, neutrons, and electrons, but really when we do that, we lose the identity of that atom. Once you start changing the number of protons you have, you change the element. If you change the number of neutrons, you change the isotope. If you change the number of electrons, you change the ion. So there's any of those variations really can alter the intent that Dalton had originally conveyed through this statement. Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. That's still true. And number 5, in chemical reactions, atoms are combined, separated, or rearranged. And of course, we know that to be true as well. Here on the slide, this is interesting. We used to do this lab, and I know I've worked it to death on labs. I think we did 4 density labs. This would have been another density lab we could have done. And we used to do this. I think I stopped doing it a couple of years ago. Mainly because pre-1982 copper pennies, as you can see here on the left side, have become much more difficult to find. I'd have to go and scour through hundreds, maybe thousands of pennies to find, maybe 30 or 40, pennies from before 1982 that are still in circulation that we could actually use to do this lab. But the bottom line is in 1982, they changed the composition of pennies. It's got, I believe, less copper in it. It's got more zinc or tin on the inside because, a copper penny is not copper all the way through. And so you could actually take pennies from before 1981 and calculate their density, and you could take pennies from after from 1981 or before, calculate their density, and you could take pennies from 1982 and after, calculate their density, and they would be different. And again, that's because copper had largely been removed because the value of copper had gone up dramatically, and it was actually costing more to make a penny than a penny is worth. I think that's still the case again today, or it's become the case again today. But nonetheless, pre-1982 and post 1982 and post pennies actually have different compositions. So if you find one in your pocket, hold on to it. It's a little bit more valuable than some of the later ones. They may actually be taken out of circulation at some point in the future because of this. All right, so let's move on. On the left side here, you see this brown powdery substance, a solid, and it's a copper oxide. It's made of 1 copper atom combined to 1 oxygen atom. That's the ratio, 1:1. And when you put a copper atom and an oxygen atom together, you get this copper 2 oxide. The charge in the copper, of course, with the Roman numerals there indicating it's +2. Oxygen, you may remember, is -2, so you have a 1:1 ratio. Now, here in these bottles, if you could imagine on the left side, you've got some copper and oxygen, pure oxygen contained inside of the stoppered container, and you've got a clump of pure cotton down at the bottom. If you could get them to react, you would actually get one of the coppers to mix with one of the oxygens, react and combine, and you'd form this black powder that you saw on the previous slide, which would be the compound copper 2 oxide. Let's take a look at this slide. Now, if you were given an example like this, you would say, does Dalton's postulates, 5 postulates, the atomic theory, is this proof of it? Does this apply, or does this violate what he had said? And when you look at this here on the left, you've got 2 green atoms, of a particular element. We'll call that element A, and you've got 2 blue atoms of element B. And then on the product side, or the right side, you've got 1 atom of element B followed by 1 atom of element A. Now, which of Dalton's postulates does this violate? Well, it really violates the one where it says, as you can see down below, atoms are neither created nor destroyed during a chemical change. If you look on the left side, the reactant side, you've got 2 A's and you've got 2 B's. And on the right side, you've got 1 A and 1 B. So where did the other A and B go? There should be 2 of each on the left side and 2 of each on the right side. But you don't. And so you actually lost some matter. It's been destroyed, you would say. And unless you could calculate this as loss altered or changed into energy, which we have no indication of that here because we're not giving any measurements, we'd have to say that this in fact does violate the atomic theory as Dalton proposed. It also kind of violates Lavoisier's conservation of mass, right? According to the conservation of mass of the reactant should equal the mass of the products. Now, clearly that can't be the case here because you don't have the same amount of product as you do reactants. And it also would, as you don't know yet, but it would also violate the first law of thermodynamics, which talks about the relationship between mass and energy, and you should in a system be able to have all the mass and energy contained in the system, either on the reactant side or the product side, both being equal or accounted for in one way, shape, or form between mass and energy. And of course, this would probably violate that as well, but we're not really given much information on the energy, but we'd have to assume that they'd be different. So, hopefully you'll get that premise, you'll understand that. We can build on that if you do not. But make sure you understand Dalton's 5 postulates very thoroughly, and you'll be able to explain whether this is something that supports his theory or something that violates his theory. So if we take a look at an example like this, where clearly you've got 2 A's plus 2 A's plus 2 B's on the reactant side, and on the product side, you would say it produces 2AB, or excuse me, A2B and plus A2B. You can clearly see that you've got 4 A's on the left, 4 A's on the right, 2 B's on the left, 2 B's on the right. And so you don't have any violations of any theories as far as you can tell here. And so this would actually be a good model for Dalton's atomic theory. Now, Dalton knew of the work of Joseph Proust, who was a French chemist, and I think Dalton was in England at this point in time. And so this was in a few years of Dalton's work. I think Proust was a little bit before that he had come up with the law of definite proportions, which stated that all samples of a pure compound contain the same elements and the same proportion by mass. You probably remember that from physical science, so I won't delve into that too much. And so that was Proust. That's his contribution. So if you think back to the 3 main ideas, the law of conservation was mass, as I mentioned earlier, was Lavoisier. And then you've got the law of definite proportions by Proust. And then Dalton built upon Proust's ideas and came up with the law of multiple proportions, which states that if you have 2 elements and they react to form more than one different type of compound, a fixed mass of one element will react with masses of the other element in small ratios of whole numbers. And so you got law of conservation of mass by Lavoisier, you got law of definite proportions by Dalton, and you get the law of multiple proportions, or excuse me, law of let me write that down before I get everybody messed up here. So you got law of conservation of mass, and that's conservation of mass, that's Lavoisier. You get the law of definite proportions, and that is Proust. So these first 2, Lavoisier and Proust, are both French chemists. And then you have Dalton with the law of multiple proportions. Now, there's a lot of going back between France and England at this period of time during the peace, prior to the French Revolution, after the French Revolution. in those brief spans of peace between France and England during the Napoleonic era. So these gentlemen were all along. Of course, Lavoisier lost his head during the French Revolution. He was guillotined because he was, apart from a brilliant scientist, he was also a tax collector who was hated by the bourgeoisie or such, and he was decapitated. Proust, I don't know what actually came of him. I think he was able to live out a full life. But these guys all actually developed these theories all within about a 10-year span of each other, if I'm correct. 10 to 15 years at most. So this was a lot of work that was going back and forth and between Lavoisier, Proust, and Dalton, either directly or indirectly. We know Lavoisier factually knew Priestley, Joseph Priestley from England, that they had met on occasion, and they had this big battle about who created oxygen, or who discovered oxygen. Priestley had done some of the preliminary work. Lavoisier was able to identify the compound, or excuse me, identify the element. So there's a big there was a big to do about that back then as well. But there's a lot of work done between France and England during this period of time in these particular areas, and communication back and forth as well. So again, law of conservation of mass, Lavoisier; law of definite proportions, Proust; law of multiple proportions, Dalton. Last slide. Okay, on the left here now, when we talk about law of multiple proportions, you could have two elements combined in different combinations, right? If you have H2O, you have water. Did it again. Sorry about that. Here we go. If I have H2O, I have water. But if I have a different combination of hydrogen and oxygen, H2O2, I now have hydrogen peroxide, and which is a very different compound. And we're kind of seeing the same thing here. In one case here on the left side, we've got a relationship of copper 2 oxide, where we've got a relationship of one copper to every oxygen. You can see they alternate. No matter which way you go, they alternate 1 to 1. But over here, you can see you get 2 to 1, right? You get 2 oxygens per. Or excuse me. Here they're using chlorine, and so let's go back and do it with chlorine and oxygen. That'll make a little more sense to you, since that's what they're mentioning down here in the footnotes. So you've got copper and chlorine, okay? So you've got a 1-to-1 ratio there, and over here you've got a ratio of 2 chlorines to every copper. So you got CuCl2. So you could have two different, so in one case you have copper 2, in one case you have copper 1. So you could have variations here of combinations of the same elements forming different compounds. And this is really where the law of multiple proportion comes into play, because if you add up the mass of the copper and divide it by the mass of the chlorine, and then you divide that ratio by the mass of the copper and the the 2 chlorines in the second example, B, Cu, and the Cul2, and you add up those masses and compare them, and then you compare the whole thing, you actually get the identification of 2 different compounds. And in one case you've got a relationship of 1 to 1, and in the second case you got a relationship of 1 to 2, which allowed them to be able to identify that, in fact, yes, you do have 2 different compounds. And that was really an eye-opening and telling event that supported, a lot of what Dalton was saying, and also what they were able to experimentally observe at this point in time. All right, that's it for section 1, and we will talk about section 2 here shortly on the next